What's fascinating here is that the sim-to-real gap, it isn't just some minor annoyance.
No, it sounds like a huge bottleneck.
It's a major roadblock in creating truly autonomous systems. You can spend countless hours training a robot in a pristine simulation, but the moment it hits a real-world situation that wasn't perfectly copied, well, that training can become surprisingly ineffective.
So how do we bridge this divide? How do we create robots that can actually learn and adapt, kind of like us?
Well, that's the big question, isn't it?
And that's exactly what we're exploring today. We're diving into NVIDIA's Cosmos-Transfer 1. Think of it as potentially a game changer in how we teach robots to see and understand the world.
And it's not science fiction either.
No, this isn't some futuristic fantasy. It was released back in March of 2025, and it's already out there on platforms like Hugging Face and GitHub.
What's particularly noteworthy about Cosmos-Transfer 1 is its core ability, generating these incredibly lifelike virtual environments specifically for robot training.
Right, it's not just about making pretty pictures.
No, not at all. It's about crafting simulated worlds so close to reality that robots trained inside them can, hopefully, transition to real-world tasks much more smoothly.
And the way it pulls off this realism is, well, pretty ingenious. It uses multiple types of visual input. It's almost like giving the AI different senses to perceive the same scene.
Yeah, like different data streams.
Exactly. We're talking segmentation maps. You can think of those as labels telling the AI, this is a table, this is a chair.
Semantic understanding.
Then there are depth maps, which give a sense of, how far away things are, kind of like our own depth perception.
Right, the 3D structure.
Edge maps define the sharp outlines of objects, and even blurred context images provide the overall layout. It blends all these visual cues
to create these really detailed virtual environments.
Yeah, and the key innovation seems to be combining these multiple senses for the AI, giving it depth, object recognition, boundaries all at once. It leads to a much richer understanding of the simulated world.
And if we connect this to the bigger picture of AI development, you can really see why this multimodal approach is so significant.
How so?
Well, traditional methods often relied on maybe just one or two of these visual inputs, right? Which limited the AI's grasp of the simulated environment. By combining these different perspectives, Cosmos-Transfer 1 allows for a much more comprehensive, more nuanced representation of the world.
Okay, so let's really dig into why this sim-to-real gap is such a problem. What were the limitations with how we used to train robots?
The limitations of traditional training, they really boil down to a few key challenges. Firstly, collecting real-world data. It's incredibly expensive, super time-consuming.
Right, I can imagine.
Just think about trying to gather enough data of every possible traffic scenario or every imaginable warehouse layout or, every potential hazard a search and rescue robot might face. It's a logistical nightmare.
Yeah, totally impractical.
Plus, in some cases, like training for dangerous situations, it's simply not ethical or even safe to collect that data in the real world.
Right. It's like trying to learn to ride a bike by only ever practicing on a perfectly smooth indoor track.
Exactly.
We might get the basic balance, but what happens when you hit a bump or have to swerve around someone?
Precisely.
Right.
And that leads right into the second major limitation, simplified simulations.
Okay.
While simulations are safer, more scalable, they often lack the intricate details and unpredictable elements of real-world scenarios.
That's sim-to-real gap again.
Exactly.
Yeah.
As we mentioned, even tiny details that a human might not even consciously notice can completely throw off a robot. Think of that self-driving car, perfect on a pristine virtual highway, but then it gets confused by a slightly shaded lane marking in reality.
Or a warehouse robot.
Yeah, a warehouse robot that can navigate a perfectly organized simulated warehouse, but then struggles when a box is just slightly out of place. These failures in unpredictable situations really highlight the critical need for more realistic training environments.
So, with those pretty significant hurdles in mind, it's exciting to see how a new approach, like NVIDIA's Cosmos-Transfer 1, is tackling these fundamental issues. What's different about its approach?
The core of its innovation lies in what they're calling adaptive multimodal control.
Okay, adaptive multimodal control.
Essentially, this means developers get much finer-grained control over how the virtual environment is generated. They can use those different visual inputs we talked about: segmentation, depth, edge maps, context images, and crucially assign different levels of importance or weights to each input for different parts of the scene.
That sounds pretty sophisticated.
Yeah.
Can you give us a specific example? How does that work in practice?
Absolutely. Imagine you're teaching a robot arm to pick up a specific pen from a cluttered desk.
Okay.
This system lets you tell the AI, pay very close attention to the pen's shape and position, using maybe the depth and edge maps with high weighting.
Right. Focus on the critical part.
Exactly. Meanwhile, the details of the cluttered desk around it, less critical for this specific task. And for the background, maybe some books on a shelf. The lighting in the room, you could allow for more variation using, say, the blurred context images with lower weights.
Ah, I see.
This way, the robot's training is focused on that key interaction, but it still gets exposed to a diverse range of background conditions. That makes it more robust in a real-world setting where, the lighting might change or the desk isn't perfectly organized.
So it's about prioritizing accuracy where it matters most for the task, but still injecting enough variability elsewhere so the AI doesn't get locked into one specific idealized view.
Precisely. NVIDIA emphasizes this spatial conditional scheme, highlighting its adaptability and customizability. Developers can really tailor these virtual environments with precision, optimizing realism for the key elements without sacrificing the overall diversity of the training scenarios.
That level of control sounds like a big step up.
It is. It's a significant step forward from traditional simulations where you often had to choose between, high fidelity in a very limited set of scenarios or broader variability but with less detailed visuals.
Now, the information we've looked at mentions this approach enables human-like learning in robots. That's a pretty bold claim.
Yeah.
Can you break down what they mean by that?
Yeah, it's important to clarify that human-like learning here doesn't mean that AI suddenly develops consciousness or, intuition.
Okay, good clarification.
Instead, it refers more to the way humans learn through variation. Think about how a child learns to recognize a dog.
Right.
They don't just see one perfectly prototypical golden retriever. They see Chihuahuas, Great Danes, Poodles, dogs of all different shapes, sizes, colors, in all sorts of settings.
Yeah, tons of examples.
And this exposure to a wide range of examples allows us to generalize our understanding. Traditional simulations often really lack this level of rich variation. You might train a robot on, say, a few dozen manually created scenarios.
Which is nothing compared to reality.
Exactly. It's a tiny fraction of the variability it'll encounter in the real world. It's like learning a new skill by only practicing the easiest version of it. You won't be ready for the real challenges.
Makes sense.
So, Cosmos-Transfer 1 addresses this by making it possible to generate hundreds, maybe even thousands, of unique photorealistic environments for the same core task. By introducing this necessary diversity, different lighting, slightly different object placements, texture variations, the AI gets a much richer training experience.
And that allows it to generalize better.
Far more effectively, yes. By training these policy models, essentially the robot's decision-making rules in these varied environments, developers can fine-tune the robot's behavior much more comprehensively. And that reduces the reliance on massive amounts of real-world data.
And this has some pretty significant implications for specific applications, right? Like you mentioned autonomous driving.
Absolutely. Take autonomous driving. Traditionally, simulating those rare but critical edge cases like encountering a really unusual road sign or navigating a complex, poorly marked intersection, maybe driving in heavy fog.
Yeah, the tricky stuff.
That's been incredibly challenging. With Cosmos-Transfer 1, developers can now generate countless variations of these scenarios. They can expose the AI to a much wider range of potentially dangerous situations without ever having to put a physical test vehicle at risk.
Which means safer, more thorough training.
Exactly. Safer and more comprehensive training, ultimately making autonomous vehicles more reliable in the real world. And it's not just about avoiding accidents, is it?
Yeah.
It's also about making the AI's behavior more nuanced, more adaptable in just everyday driving situations.
Right, smoother interactions.
Precisely. And the model also significantly enhances the training of those policy models we mentioned. By training these decision-making systems in the varied high-fidelity environments generated by Cosmos-Transfer 1, developers can fine-tune behavior more comprehensively, cutting down on the need for huge real-world data sets.
Which speeds things up.
It speeds up development, and it makes the resulting AI systems more robust, more responsive to real-world complexities. So again, it's not giving robots human-like thinking, but it is providing a training environment that mirrors how humans learn through exposure to endless variations. That leads to more adaptable and reliable AI.
Okay, so we understand the why behind Cosmos-Transfer 1. Now let's delve into the how. What's the core technology making this possible?
At its heart, as we've touched on, is this concept of adaptive multimodal control.
Right.
It's the system that lets developers strategically apply those different visual inputs, depth maps for 3D understanding, edge maps for sharp boundaries, segmentation maps for identifying what's what, and those blurred context images for the overall layout.
Each contributing something unique.
Exactly. Each input gives a unique piece of spatial information, allowing the model to create environments that are both visually accurate and diverse.
And the secret sauce seems to be in how these inputs are combined and controlled with that spatial weighting system you mentioned.
That's it.
Yeah.
This allows developers to define literally pixel by pixel how important each visual input is. So like in our pen example, you could assign a high weight to the depth and edge maps right in the area where the robot interacts with the tool, ensuring super precise rendering of that interaction.
Okay.
But then in the periphery of the scene, you might lower the weight on those inputs and allow more variation in things like lighting, surface materials, making the environment feel more natural, less artificial.
That level of granular control sounds incredibly powerful.
Right.
Really flexible for different training tasks.
It is. And of course, to handle the massive computational demands of generating these complex environments, NVIDIA has leveraged its powerful hardware.
Makes sense.
They scaled the model using their GB200 NVL72 rack. And in their tests, they saw a remarkable 40 times speed up when going from just one GPU up to 64 GPUs.
40x.
Yeah. This kind of hardware muscle lets the system generate these realistic simulations incredibly fast, allowing developers to rapidly train and test their robot AI. They actually achieved near real-time simulation, generating 5 seconds of photorealistic video in just over 4 seconds.
Whoa, that kind of speed must be a game changer in itself. Faster iteration means quicker progress, right?
Absolutely. Fast simulation isn't just about convenience, it fundamentally changes the development workflow.
How so?
It allows for more frequent iterations. You can train your models, see the results, make adjustments, retrain much more quickly. This rapid feedback loop leads to faster model updates and, crucially, quicker identification and correction of errors in the AI's learning process.
So this isn't just some theoretical advancement. It has tangible benefits for developers right now, letting them work much more efficiently.
Precisely. And we're already seeing the potential impact of Cosmos-Transfer one across a whole range of industries that are increasingly relying on physical AI systems.
Okay, let's dive into some of those real-world applications then. Beyond autonomous vehicles, where else is this tech really going to make a difference?
Well, industrial robotics is another key area. Think about factories, warehouses. Robots often have to operate in dynamic workspaces.
Things are always changing.
Exactly. Tool positions change, lighting fluctuates, human workers are moving around. Training robots in richly varied yet physically consistent simulated environments lets them adapt to these real-world complexities much more effectively. That leads to increased reliability, less downtime.
That makes perfect sense. A robot trained only in a static, predictable setup is going to struggle when things shift on the factory floor.
Exactly. And in warehousing and logistics, too, robots sorting, transporting, retrieving items, they frequently encounter unpredictable layouts, unexpected obstacles, varying shelf configurations, shifts in lighting.
All sorts of chaos.
Pretty much. By simulating these conditions, Cosmos-Transfer one can help reduce system failures, improve the overall efficiency of these operations. It's almost like giving the robots a broader range of life experience in a virtual warehouse before they ever navigate a real one.
That's a great way to put it. And what about applications in more, maybe high-stakes environments, like search and rescue?
Oh, absolutely crucial there. Training robots to navigate, say, collapsed structures, rugged terrains, or fire-damaged areas in the real world is obviously incredibly dangerous.
Yeah, you can't just send teams in repeatedly.
Right. Cosmos-Transfer one allows developers to create realistic simulations of these hazardous environments, enabling robots to be trained effectively without putting human personnel at risk.
And even in fields like healthcare, where precision and reliability are just paramount. It sounds like significant potential there, too.
Absolutely. Medical robots often need extremely high levels of precision, right? And their operating environment can vary significantly. Lighting, equipment arrangement, even subtle differences in patient anatomy. Creating simulations that capture this variability can improve the reliability of these robots before they're ever used in a live medical procedure.
Wow.
Across all these sectors, really, the fundamental value proposition is the same. Giving AI systems the chance to learn and adapt in environments that closely mirror real-world complexity.
but without the costs, risks, and limitations of only using real-world data.
Exactly.
So Cosmos-Transfer One isn't just a standalone tool. It's part of something bigger at NVIDIA, right? You mentioned a Cosmos platform.
That's correct. Cosmos-Transfer One is a key piece of NVIDIA's broader Cosmos platform. This platform is a collection of what they call World Foundation Models, or WFMs.
WFM's World Foundation Models.
Yeah, AI models designed specifically to understand and simulate the physical world. This whole initiative really reflects NVIDIA's increasing focus on physical AI.
Physical AI.
Yeah.
AI that interacts with its surroundings.
Exactly. Developing AI that can intelligently interact with its physical surroundings.
And there are other models within this Cosmos suite that complement Cosmos-Transfer One.
Yes, there are. For instance, there's Cosmos Predict One that's focused on world prediction and generation, allowing AI to anticipate how environments might change over time and space.
Okay, predicting the future state.
Kind of. Then there's Cosmos Reason 1, which aims to give AI systems a form of physical common sense, understanding cause and effect, object permanence, spatial relationships.
Things humans take for granted?
Pretty much, yeah, all crucial for effective real-world reasoning. Think of the Cosmos platform as NVIDIA's complete toolkit for building virtual worlds for AI. Cosmos-Transfer One helps the AI see these worlds realistically. Other tools in the kit help the AI predict changes and understand basic physics within them.
It sounds like NVIDIA is building a really comprehensive ecosystem for developing and testing physical AI in these virtual environments.
Precisely. And what's quite significant is NVIDIA's open approach to this technology.
Oh, yeah. How so?
They've made these pre-trained models accessible under their open model license, and they've provided the training scripts under the Apache 2.0 license.
That's big.
It is. It's a clear signal of their intention to accelerate global innovation by putting these cutting-edge tools directly into the hands of developers and researchers everywhere.
That open approach could really foster rapid progress, couldn't it? More collaboration, people building on this tech.
Absolutely. Together, these Cosmos models are supporting an industry-wide shift toward multimodal simulation environments. We're seeing this growing recognition that AI systems need to integrate various data types, visual, spatial, semantic, physical, to truly understand and operate effectively in the real world.
It's not just about vision anymore.
No, not at all. As AI increasingly relies on inputs from diverse sensors, cameras, LiDAR, motion sensors, spatial maps, foundational models like Cosmos-Transfer One are becoming absolutely central to building intelligent, adaptive systems that can reliably function in our complex world. Cosmos-Transfer One really does represent a significant step forward in how we train robots.
So, to sort of bring it all together, the big takeaway here seems to be that Cosmos-Transfer One offers a really innovative way to train robots. Instead of relying on limited, idealized simulations or, expensive, potentially risky real-world data, it allows for creating highly realistic and incredibly varied simulated environments. This mirrors the kind of diverse experiences that humans take for granted when learning.
Right.
And that ultimately leads to more robust and adaptable AI.
Exactly. It's not about magically giving machines human-level intelligence, but it is about providing them with the kind of rich, varied sensory input during training that lets them generalize their learning and handle the unpredictable nature of the real world much more effectively. This shift in training methodology, it has the potential to significantly impact how AI learns to operate in our world.
And that leads me to a final thought, maybe for our listeners too. Consider how this enhanced capability for realistic simulation might accelerate the deployment of robots in areas of our lives that we haven't even fully imagined yet. What new possibilities, or perhaps even new challenges, might arise as robots become more adept at navigating and interacting with our complex world, thanks to this more human-like learning experience and simulation?
That's a great question.
It's definitely something to think about beyond just the specific applications we've discussed today.